Hello everyone, and welcome back to the channel. Today's video is about pipelining, a fundamental concept in modern processors to increase instruction throughput by overlapping the execution of multiple instructions. Different methods can improve the speed of a program. One way is to use faster circuits and hardware. Another way is to rearrange the hardware in such a way that more than one operation can be performed at the same time, which is called pipelining. Pipelining breaks the execution of each instruction into smaller steps, such as fetching, decoding, executing, and writing back, allowing the CPU to work on different parts of multiple instructions simultaneously. Thus, new instructions can begin before the previous ones have completely finished, making the overall process faster and more efficient. Most modern computers use Superscalar processors. These processors have multiple execution units that allow them to dispatch multiple instructions to appropriate functional units within the CPU. Let us take 4 instructions, I1, I2, I3, and I4. If these instructions are executed sequentially, it would look like this. If each instruction takes 4 clock cycles to execute, the whole operation would take 16 clock cycles. Since machine instruction can be broken down into different phases in its execution, we can alter the hardware so that the processor can execute each phase independently. For example, when an instruction is in the execution phase in the ALU, the circuit that fetches the instructions is idle. So, we can use the time the ALU spends executing the first instruction to fetch the second instruction. If each phase can be processed independently, the execution sequence would look like this. Thus, the number of operations performed per second increases, even though the time required for each operation remains unchanged. This technique is called pipelining. To implement this pipeline, we design the hardware as shown here. Each execution step is handled by a dedicated hardware unit with a buffer unit between each phase. Since the instructions are divided into different phases, we can execute multiple instructions simultaneously. 2 critical factors contribute to the efficiency of the pipeline. First is the role of the compiler. Optimizing compilers are designed to generate highly efficient machine code from source code. Such compilers rearrange the sequence of operations to maximize the benefits of pipelined execution. Various problems called hazards can cause performance degradation in pipelined processors. Compilers also provide means for mitigating these problems. The second is the role of the cache memory. Since memory fetch can require as much as 10 times longer than typical processor operations, such as adding numbers, the fetch operation could defeat the whole purpose of pipelining. To solve this problem, we use cache memory inside the CPU with the same access time as the other processor operations. Even though the introduction of multiple pipeline stages increases the speed of the processor, there are specific conditions that can disrupt the smooth execution of instructions in a pipeline. Conditions that prevent the next instruction in the instruction stream from executing during its designated clock cycle are called hazards. They can cause delays and require special handling in pipelined processors. There are 3 types of hazards: data hazards, control or instruction hazards, and structural or hardware hazards. The first type of hazard is the data hazard. A data hazard is a situation in pipeline processors where instructions that are close to each other in the instruction pipeline depend on each other for data. This dependency can cause delays or errors if one instruction tries to use data that has yet to be fully processed or written back to the register by a previous instruction. Data hazards are generally categorized into 3 types. The first type of data hazard is the read after write hazard. It occurs when an instruction requires reading a register that a previous instruction has not yet finished writing to. In this example, if instruction 2 is executed before instruction 1 finishes, it could read an outdated value of register R1. To prevent this type of hazard, we can use 2 methods. The first method is introducing a delay between the 2 instructions so that instruction 1 is completed before instruction 2 starts. Many processors have an instruction that introduces a delay, often called a NOP or no operation instruction, which makes the pipeline wait for some time. By placing an NOP instruction between the dependent instructions, the pipeline is delayed, allowing the first instruction to be completed, thus resolving the dependency. While NOPs can help prevent data hazards, they also reduce efficiency by stalling the pipeline without performing any useful computation. For this reason, modern processors often use more advanced techniques to minimize the need for NOPs and increase instruction throughput. Operand forwarding is used by most modern processors to mitigate read-after-write data hazards. In typical instructions, before the write cycle is executed, the result is already available at the ALU in a buffer. The read-after-write hazard occurs because, although the first instruction has been completed and its result is stored in the ALU buffer, that result has not yet been written to the register. As a result, when the second instruction attempts to read the value from the register, it reads an incorrect value. To resolve this issue, we should retrieve the correct value directly from the buffer instead. The write cycle spends one more clock cycle to write the output to a memory location or a register. So, we can use this time to direct the buffer's content back to the ALU immediately. This technique of directing the result directly back to the ALU is called operand forwarding. The CPU cannot always use operand forwarding, so it must detect when forwarding is possible and when it is not. The CPU decides whether to use forwarding based on dependency detection logic in the pipeline control unit. The second type of data hazard is the write-after-read data hazard. It occurs when an instruction writes to a register before a previous instruction has finished reading from it. In this example, instruction 2 depends on the value of R1 from instruction 1, and instruction 3 overwrites R1 with a new value. If the third instruction is executed before instruction 2 is completed, it introduces a write-after-read hazard. Write-after-read and write-after-write hazards arise due to out-of-order execution. Out-of-order execution is a technique used in modern processors to improve performance by allowing instructions to execute as soon as their operands are available, rather than strictly following the program's original order. While this approach increases execution speed, it can introduce data hazards. Out-of-order execution relies on two key structures to manage and optimize instruction execution: instruction window and reorder buffers. The instruction window is a buffer that holds a set of instructions that are ready to be executed. The CPU checks the instruction window to find instructions whose operands are available and can be executed out of order. This way, instructions that do not have dependencies can proceed without waiting for earlier instructions to complete. The reorder buffer is a crucial component that ensures the instructions are committed in the correct order, even if they are executed out of order. It helps maintain program correctness by storing the results of executed instructions until they can be committed in the original program order. Now let us look at a step-by-step process of how out-of-order execution works. Consider 3 instructions where instruction 2 depends on the result of instruction 1, but instruction 3 does not depend on the result of instruction 2. First, all 3 instructions are placed in the instruction window. In the first step, the processor executes instruction 1 and stores the result in the reorder buffer without committing it. Instruction 2 needs the result from instruction 1, so it waits for instruction 1 to complete. Instruction 3 is independent of instruction 2, so the processor may execute it before instruction 2, depending on its scheduling. However, its result is stored in the reorder buffer and has not yet been written to its final destination. Once instruction 1 is complete and its result is available in the reorder buffer, instruction 2 can begin execution and store its result in the ROB as well. Finally, during the commit stage, instructions are written to their final destinations in the original program order. In this way, even though the instructions are executed out of order, the computer tries to make sure that the program order is maintained. However, even though the ROB holds the results temporarily before they are committed to the register file, it doesn't prevent data hazards during execution. This is because the ROB does not track or resolve dependencies between registers during execution. This is where register renaming comes in. Register renaming allows the CPU to avoid conflicts by assigning different physical registers, eliminating the possibility of writing to a register before it's read. Logical registers are what the programmer sees and uses, while physical registers are what the CPU uses behind the scenes to optimize performance. Now, let's take our example and see how register renaming works. A physical register file, PRF, dynamically renames R1 to avoid conflicts as shown here. Now the renamed version of the code would look like this. The logical register R1 is now mapped to different physical registers, P1 and P2. Instruction 2 now reads from P1, which holds the correct value from R2. Instruction 3 writes to P2, which does not affect the previous read from P1. Once execution is complete, The reorder buffer ensures that instructions are finished in the correct order so the CPU behaves as if it executed them sequentially. It also makes sure that the correct value is written back to the logical register, R1. The third type of data hazard is the write-after-write data hazard. It occurs when two instructions try to write to the same register and the pipeline performs them out of order. In this example, both instructions write to the register R1. If instruction 2 writes to R1 before instruction 1, we have a write-after-write data hazard. This type of data hazard can also be resolved using register renaming, as shown here. Each instruction writes to its own physical register P1 and P2, and when the results are committed, only the latest valid result updates R1. Before wrapping up, let us look at one more key idea: the difference between true and false dependencies. Read-after-write data hazard is called a true dependency, whereas the other two hazards are called false dependencies. In this example, if instruction 2 executes before instruction 1 finishes, it will use an incorrect value of R1, leading to an incorrect result. This is called a true dependency because instruction 2 depends on the result of instruction 1. It is also called a forward dependency because the dependency flows forward in program order, meaning instruction 1 must execute first before instruction 2 can correctly execute. In contrast, if instruction 3 executes before instruction 2 in this example, it creates a false dependency or name dependency. This occurs because the instructions reuse the same register rather than due to an actual data dependency. Instruction 2 and 3 do not depend on each other. The conflict arises solely from register reuse. That is why it is classified as a false dependency. To summarize, there are three types of data hazards. The first is the read-after-write hazard, which occurs when the processor reads an outdated value from a register while the correct value is still in the ALU buffer. This is known as a true dependency because it happens when a later instruction executes before a previous instruction has finished, leading to incorrect data being read. The other two hazards, write after read and write after write, are caused by out-of-order execution, a feature in modern processors that allows instructions to execute in a different order than they appear in the program. These are considered false dependencies because they arise from register reuse rather than an actual data dependency. Fortunately, register renaming eliminates false dependencies by assigning different physical registers, ensuring correct execution order. Thank you for watching the video. I hope you learned something today. Have a beautiful day, and see you in the next video.